Hello. Yes, so today, just a minute, let me allow everyone to join. Yes, so today we will cover the topic about network layer in the session 6 of NPTEL PMRF live session. So in this course, in this lecture, we will cover the details about the network layer. So till now we have studied about the application layer and the transport layer, and beneath that layer comes the network layer. So it is the layer 3, which is known as the network layer. So yes. So as we have studied about the transport layer and the services which are being provided by the transport layer, so now we will discuss what are the services which are being provided by this network layer. So as we know that transport layers offer, as a TCP protocol, offers a reliable data delivery. However, in the network layer, it only ensures the datagram delivery that might be unreliable or a reliable delivery. So the network layer just ensures that the data is delivered. That means if you want to send a data from one device to another, so the network layer ensures to make a connection between both the devices and allow the data to get transferred from that device to another device. So it tries to locate the location of the another device from the source to the destination. So another service which is being provided by the network layer is the routing mechanism. So there might be a possibility that in the network, like in a network of any of the systems, there are multiple routes. As we have already seen that there might be a multiple route in that network. For example, say we have this node, then another node, then this node, and there is a path from this to this node, and there's another path which is from an intermediate single node to this corresponding node. Okay, so and there is another path through multi-hop, 1 2, then 3, then there are 4 nodes, then there are 5 nodes, and then this. So in this way, we see that which is the best possible suitable path that can be taken uh, for this datagram delivery. So that is possible using this network layer. So it helps to route the packet from one source to the destination, and it allows it provides the protocol which helps to route that particular packet. So there might be a possibility that the packet follow this corresponding path. There might be another possibility that the packet follows this path, and there might be another possibility that the packet follows this path. So at a certain moment, there can be a trade-off that we need the earliest delivery, and at the certain moment, if there is a trade-off that there is no constraint about the earliest delivery. However, there are a lot of congestion or the nodes get broken at this end. So say for example, if we want the shortest delivery and we are sending through this node, but however, at some point of time, this node gets disconnected or this node is disrupted due to some reason. So for that reason, there is a rerouting which is being controlled by the network layer protocols. This is the another service that it offers. And then there is a third service which is known as the addressing, which talks about the how to give the address to a particular source and the particular destination, and thereby give the address to the host in that node, in that network, and then host in the destination network. So all the addressings are being done by the network layer. I hope this is clear to everyone. So these are, I just explained the broader services which are being provided by the network layer. So we will discuss the details about these services later on in the subsequent lecture. So the basic principle that is about the internet architecture, that it is organized in a very hierarchical fashion. Say, for example, we have a network of a institute where there is one lab and then there is another lab, that is one software lab and another software lab. So this network is connected by this router, which is known as the layer 3 switch, as the network layer is the layer third layer. So the switch in the network layer, which tries to connect to one lab to another lab, one local area network to another local area network, is the router, which is all known as layer 3 switch. Okay, it is known as L3 switch. Okay. So in this manner, here there is LAN 1 and this is LAN 2. So the software lab LAN 1, this is in local network, local area network 1 and local area network 2. So they want to communicate with each other. These devices want to communicate with each other through a router. This is a single network. Then we have a broader network which contains multiple network. For example, that was the earlier network of computer science department. There's this another network of some another department, say electrical. So the department wise also they want to communicate. That is also being done by the router. That is the L3 switch. So the earlier was this inter network on the same inter network communication. Then it is between the two departments in a particular college network. So then comes the third hierarchy, that we say that this was the first second hierarchy. Then there is a third hierarchy in which there is a one college network which has multiple departments, and in that particular department they have multiple local area networks. Similarly, there is another college network with the multiple departments and their multiple local area networks. So this complete architecture, they communicate with each other, and this is known as the ERNet network architecture. So then there is the fourth layer in which there are multiple institutes which are incorporated in a particular network, and there is another network in which there are BSNL public ports or BSNL public devices. So this is controlled by the service provider, that is Bharti Airtel network. For example, there is a Airtel network at a global level which tries to provide the network to the individual institute. So there is a cluster of these institutes which is composed under a single network, and that network service provider is Bharti Airtel network. So this is the hierarchical fashion that we follow in the network architecture. So now these are there is a term which is known as autonomous systems. So what basically are these autonomous systems? These systems are a set of LANs for an administrative domain identified by a unique autonomous system number, and the routing policies are controlled by a single administrator. For example, we had the local area network, which is composed of a common three-layer gateway. So that also is an autonomous system which tries to control the whole architecture and the routing policies of that particular network. Then there is another network of the colleges where all the colleges were composed, like this Bharti area Airtel network. This is again itself an autonomous system which has different policies and different routing architectures. Okay, in this way, individual autonomous systems, have their unique autonomous number and the routing policies, which are controlled by a single administrator. How do they make a connection with each other, and how do they transfer the data from one source to another destination? Okay, so in this internet architecture, this for example, there are multiple tiers of network which provides services to each other. So an autonomous system provides internet connectivity to another group of autonomous systems or end users, that is known as internet server provider. For example, we have this internet users which get the internet services from tier 3, that is multi-homed IP. Then there is tier 3 which gets its services from tier 2 ISPs, and then there is tier 2 ISP which gets its service from tier 1 ISPs. Okay. So in this fashion, in the network there are multiple internet service providers which provide services to one another and each of the mm, systems are known as those autonomous systems. So they get services from the tier above them. So now how we can peer between the internet service providers. So there are the local ISPs located at the bottom. So each of these local ISPs are controlled by the regional ISPs. So these regional ISPs connect to each other for private peering. So for example, there is a case like we have this two network service providers, say Jio and Airtel, and you have seen there are multiple times that they provide offers that if you buy some Airtel offers, you will get a Jio SIM free, or you buy a Jio SIM, you will get an offers on Vodafone, etc. So this is being controlled by the private peering. So these networks, regional ISPs, interconnect with each other through private peering. And with the help of this peering, they try to increase the sale or increase the reach of that network by giving multiple offers and collaborating with each other. Just similar with the case of collaboration that we do in our day-to-day life. Then above the regional ISPs, we have the network service providers. That is the global server, which provides the networks, which provide the services. And there are a lot of peering connections in between them. And finally, above them are the IXPs. So this is how the communication is taking place between the two nodes over this internet service providers. So there is this machine at the local ISP, which then gets a service from local ISP. Then it asks the regional ISP for the service, then the national ISPs for the service, then the transit ISP, which communicates with other transit ISPs. And then it again provides service to the national ISP, then regional ISP, then local ISP, and then to the destination device or system. So this is how the hierarchical communication between two nodes over the internet server providers takes place. So this is the broader network architecture. If anyone having any doubt, you can ask till now. Okay, so now we will see the IP addressing. So in this whole lecture, firstly, currently we are discussing about the IPv4 architecture and how the IP addressing takes place. We'll see that. So for the IP addressing, we need to forward data packets from one network to another network via intermediate networks. So for example, the host 1 wants to communicate with host 2. So host 1 has AS10 as address and host 2 has AS12 as an address. So the address should identify a network as well as the host inside a network. For example, there is this network AS10 which has multiple hosts, host 1, host 10, host 2, host 3. So there should be the particular host address and the network address which should be with the at the address at the time of communication. The address should identify network as well as the host inside the network for a proper communication challenge. So addressing is divided into two parts as we have seen currently. One is the network address and another one is the host address. So here we divide the address space that is 32-bit in IPv4. Here we have considered IPv4 architecture among network address and the host address. So previously, the architecture which was followed or addressing scheme which was followed is known as classful addressing, where there is a fixed number of bits for the network address and the host address. So in classful addressing, there are multiple classes which are divided based on the number of bits allotted to the network and number of bits allotted to the host ID. So there are 5 different classes: A, B, C, D, and E. So how do we identify the class? So we use the initial few bits of that class to identify a few bits to identify which class it belongs to. So first class A, if the initial first bit is 0, that means it belongs to all the networks and the host IDs belongs to class A. So the corresponding IP address is 1.0.0.0 to 127.255.255.255. That means how we generate 127 is initial bit is 0, then all other bits might be 1, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. Yes. So this makes it 127. Okay. So if the first bit is not 0, that means it is 1, and the second bit is 0, then it belongs to class B. So the address starts from 128.0.0.0 to 191.255.255.255. So then there is a class C, in which if the first bit is 1, the second bit is also 1, not 0, and the third bit is 0, then this is class C network. Then again, class D, the third bit is 1 and the fourth bit is 0, then it is class D network. And then all the 4 bits are 1, which belongs to class E network. Okay. So we will see these A, B, and C in the subsequent lecture. But what is exactly D and E? So in D, there are all the other addresses which are ranging from 224.0.0.0 to 239.255, 255, 255. That means it is a multicast address. That means it is within a network address. That multicast means that if you want to send data within a internal network to all the devices in that internal network, that is known as the multicast. For example, in the same software lab. And then there are other bits in class E, which are reserved for future use, which are not of any use for now. So I think all of you know from the lecture what is 250, how this means 255, 255, 255, and 255. If anyone is unaware of this, you can ask now in the chat. You can always post. So what is a network address? The network address is to identify a particular network. So all zeros in the host address, that means the network address. So for example, if we consider this class A, the initial bit is 0, and this is the host. This is the network ID, say 111.111.0. So all the other bits are of the host bit. So okay, you can see here, I didn't mention this. So apart from this, there is this case that for network for class A, there are the network bits allotted are 7. Like initial bit is 1, and then there is this another 7 bits which are being allotted for network, and the remaining 24 bits are allotted for host. Okay. So then this class B, there are 2 plus 14 bits which are allotted for the network ID, and there are the 16 bits which are allotted for the host ID. Then in class C, there are 3 plus 21 bits which are allotted for the network ID, and this 8 bits are allotted for the host ID. Okay, so when we see how many multiple networks are possible here, that means here the multiple networks possible are 2 to the power 7. How many multiple networks are possible here? 2 to the power 14, because 2 bits are reserved. Here 2 to the power 21. However, if we want to know how many hosts are present, so it is approximately 2 to the power 24, but not exactly 2 to the power 24, because some bits are reserved that we will see in the next slide. So here also it is approximately to the power 16, but not exactly. So what is the reason behind there are some addresses which are reserved? That there is one address which is known to identify that particular network, that we belong to that particular network. So if there is some in class A, there is a 7-bit which is allotted to the network ID, and all the other host bits are 0. That means it identifies that particular network. That means with this as this 126.0.0.0, that means we are in a particular network. That is the network ID of that particular network. Similar in class B, there is the initial bits are 10, and all other remaining bits are for network ID, the 14 bits. And then all the other host bits are 0. That means 189.233.0.0. So this is the network ID for this particular network. So this network ID is reserved for the network ID where all the host values are 0. So that means 1 is reserved for the network ID. One address is reserved for network ID. Okay. So another address which is reserved is known as the broadcast address. That means it sends the data to all the hosts of that network. So the broadcast address is the address where all the host bits are set to 1. That means all the host bits are set to 1. Here this 126.255.255.255. And similarly, for class B, here 189.233.255.255. So then 1 is reserved for broadcast address. Okay. So that means how many total number of hosts possible is 2 to the power 24 minus 2. That is 1 for the network ID and 1 for the broadcast address. Then this was for class A. Then for class B, we have 2 to the power this 16 minus 2. Okay. For class C, similarly, it is 2 to the power 8 minus 2. So these are the valid hosts that can be there in class A, B, and in class C IP address. So if this question is asked, you can answer in this way. I think this question we have already seen in the very first lecture where it was asked. So at that time, the classless addressing was not discussed. So now this is the exact idea of the classless addressing. So if anyone having any query, you can just ask now, because we will be having questions based on this further. Okay. Okay, so sometimes it is the case that in when we are giving the host IDs, so only for example, there is a question that you have total number of 255 hosts in a network. So which IPv4 address class will you use? Class C or class B? So in class C, total number of possible hosts are 2 to the power 8 minus 2. That is 2 that means 255 minus 2, that is 253. Okay, so 253 possible hosts are there. However, we need 255, so class C is not possible. So then we come to class B. There are total number of 2 to the power 16 minus 2 addresses of the host possible. However, we only need 255 hosts. So all the other address spaces are unused, and there is a huge address space which is getting lost and unused. So this is the overhead for the address spaces. It will be occupied, but it will not be used. So for that purpose, we use the concept of subnetting and supernetting in classless interdomain routing. So it means to split a larger network or to combine multiple small networks for efficient use of address space. So subnetting is to divide a larger network into multiple smaller networks for the optimal use of address space. And supernetting is combining multiple smaller networks into a single larger network for efficient use of the address space. So for supernetting and subnetting, we need to know the concept about subnet mask, which denotes the number of bits in the network address field. So currently we had network prefix and the host number. So now we have the network prefix and the host number is divided into subnet number and the host number. So here we can see that, for example, here this is the IP address and we want to see what is the subnet mask or subnet address of this particular IP address. So this was the uh, for till here we want the subnet. So all the other bits are reserved for the host bits. So then the subnet mask will be all ones at that particular position, and all the other host addresses are 0. So we write the IP address for subnetting, the subnetting location as 191.180.83.235/12. That means 12 means here this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here, till here we have the subnet mask. So the initial 12 bits are for the subnetting. The first 12 bits are the network address and the rest bits are the host address here. And the subnet mask is 255.240.0.0 here, 255.240.0.0. So here we can see in a real world that whenever we are connecting to a network, we see that IP address is this and this is the subnet mask given to it. So all the till here this position we have all ones. So this is till the 24 bits. So this is the subnet mask for this particular IP address. So how to divide a network into subnets? So let the IP address of a network is 203.110.0.0/16. So we want to divide this network into 3 subnets. Okay, so we need 3 bits for the subnet. Why not 2? So if we want to divide it into uh, this three subnets, then why not 2 bits will cover the purpose? So the reason behind this is that we normally avoid all zeros and all ones subnets because that is again the network ID and the broadcast ID. So if we give it as 2 bits, so it is 0 and 0. That will and all the other trailing are 0. That means it will be the network ID. And if we give 2 bits as 1 1, then all the others are 1. That will give the broadcast ID. So for example, here we have 192.168.0.0/16. So if we give 1 bit for the subnet, say this is 0, and all the other bits are also 0. So this will be the network address for that particular set subnet, and that this network address for the particular subnet and the original network ID will be identical. So there will be no difference between the subnet and the network, original network. And similarly, if we place 1 bit here and as 1 and all the other bits as 1, so that will be the subnet ID will be equal to the broadcast address of that original network. Okay, so in this manner, we cannot take 1 bit for classification or subnetting, or we also cannot use 2 bits because these two combinations are used for the network ID and the broadcast ID, and only two combinations are remaining, 10 or 01, which are for the which are only serving the purpose for two subnets. However, we need three subnets, so for the purpose of three subnets, we use 3 bits. That is 100, 101, and 110. So this is the broader idea that if we have to divide the network into three subnets, then we use the 3 bits for the subnetting. So rest 16 bits were for hosts. So the remaining 30, if 3 bits are used for subnetting, so the remaining 13 bits are used for addressing the host of those particular subnets. So now the subnets are 203.110.128.0/19 and 203.110.160.0/19 and 203.110.192.0/19 as given 102 here, then 1012 here as 160, and then 110 as 192. So now we see an example here. I think this is already being covered in the course as well. So I'm just repeating those concepts, briefly revising those concepts. So you have a CSE department with 2000 hosts, BG SOM with 500 hosts, and EE department with 500 hosts. So you want to give the addressing for all of them with the help of this 203.110.0.0/19. So for the 500 host, 2 to the power 9, that means will serve the purpose. 9 bits will serve the purpose. And for 2000 host, 11 bits will serve the purpose. So 19 means the remaining bits are, as we see, 13. So for 11, this if we give this 11 bits for the host, then we have the two remaining bits, and we have seen if we want to create three different subnets, 2 bits doesn't serve the purpose. So for that we need to think an alternative. So an alternative to this is supernetting these two networks and then create a subnet between this network and this another single supernetted network. So we have two options left for identify that okay. So now if we combine both of these network, there will be total 1000. That means 10 bits are reserved for the host. So the remaining 3 bits can be occupied for this subnetting here. So CSE is for 11 bits and VGSOM plus EE is done in 10 bits. So the network address here is 19. So if we give 2 bits, so that means initially 2 for 11. If we consider 2 bits, one will be 0, 1 and another will be 1, 0. Only those combinations are possible. So the CSC network address can be 1, 0 and the VGSOM address can be 0, 1. VGSOM plus EE network. So that now it leads to initial 2 bits are occupied for subnetting these both networks. And these are the addresses. Now, if we want to again categorize between this VG SOM and EE, then we occupied the next concurrent bit. That is uh, again 1, 0, next 2 bits will be occupied because we have in all 2 bits remaining. 9 bits only are occupied for this. So 1, 0 and 0, 1. So 1, 0 is given to VGSOM and 0, 1 is given for EE network. So this is how we do the supernetting and subnetting. That means classless intercommunication. CIDR example. So I hope everyone is clear with this till now. Okay, so currently we pause till here. And firstly, I will be discussing the last week's assignment, which was given to you. I want everyone to be a bit interactive and just answer the questions as you have already solved this week's assignment. So consider the following statements. One, the UDP is a wrapper of the IP layer. Second, TCP is suitable for short message transfer where reliability is not concerned. Which of the following statement is or are correct? I hope my voice is audible to everyone. So I request all of you to be a bit interactive and answers the question. Okay, so Priyesh, can you tell what is the answer? Priyesh, can you tell what is the answer if you are in the meeting? Okay, so the correct answer is A, that UDP is a wrapper of the IP layer. UDP is suitable for short message transfer where reliability is not a concern. In contrast, reliability is a major concern for TCP that we already know. So your second one is wrong. So question number 2 is that when the select system call returns 0, A, when the error is encountered. Second, the call timed out without any event ready for sockets monitored. 0 is the number of sockets that have events pending, or OS kills the process. Yeah, so right. All of you are right. Correct answer is B. When select returns 0, it indicates that the call timed out without any event ready for sockets being monitored. So the next question is that when you create a socket as S equals to socket domain type protocol, why do you set the value of the protocol parameter as 0? Yes, everyone is right. So system selects the default protocol number for the domain and socket type requested. So another question is sock stream represents. Yes, the sock stream represents TCP based stream socket. So next is socket addresses. Yeah, so the socket address is a combination of IP address and the port address. So another question is UDP does not have flow control and congestion control mechanism. And UDP is suitable for the purpose where error checking and correction is less important than timely delivery. So which of the above statements are true or false? Yeah, right. Both the statements are true. So next question is packet integrity can be checked by checksum mechanism. Yeah, it is true. So now consider the following statements regarding the slow start phase of TCP congestion control algorithm. Note that congestion window CWND stands for TCP congestion window. The congestion window increases linearly after every round trip time till threshold. So A, is this statement true or false? Yes, so it is false that the congestion window is increasing linearly. So each time an acknowledgement is received by the sender, the congestion window is increased by one segment. Thus, congestion window increases exponentially on every round trip time. So here is the next question. Consider a TCP connection in a state where there are no outstanding acknowledgements. The sender sends two segments back to back. The sequence number for the first and the second segments are 230 and 290 respectively. The first segment are lost, but the second segment was received correctively by the receiver. Let X be the amount of data carried by the first segment and Y be the acknowledgement sent by the receiver. So the value of X and Y are. Yeah, so the answer is D, that the sequence number of the first segment, that is 230, and the sequence number of the second segment, that is 290. So from here, the range of sequence number contained in first segment is 230 to 289. So total number of sequence number contained in the first segment are 289 minus 230 plus 1, that is 60. And TCP assigns one sequence number to each byte of data. Thus, the amount of data in the first segment is 60 bytes. Okay, so now on receiving the second segment, receiver sends the acknowledgement asking the first segment only. This is because it expects the first segment first. So receiver keeps sending this acknowledgement until it receives the first segment correctly. So thus the acknowledgement number is equal to the sequence number of the first segment, that is 230. So the option is D, that is the size and the acknowledgement number. I hope everyone is clear with this. Okay. So in TCP congestion control mechanism is triggered once A, the one duplicate acknowledgement is received. B, after a retransmission timeout. C, three duplicate acknowledgement is received. D, no duplicate acknowledgement is received. Yes, so the correct answer is both B and C. TCP congestion control mechanism is triggered in two situations when retransmission timeout and three duplicate acknowledgement is received. So, okay, so fine, we end this. Now we again start with the remaining part of our lecture. So anyone having any confusion till now? Any questions? Okay. So the issue that is with the IPv4 addressing is that the address space is very limited. So there we have multiple number of devices and the network equipment in today's scenario. These devices are also increasing day by day. So the address spaces in the IPv4 addressing are very limited. That is only for class A, B, and C, and class D and E are for reserved and some multicast purposes, which are also not utilized as the network addresses and the host addresses. So a large number of addresses are wasted or remain unutilized. That means in class D or E. So the solution is to make the addresses reusable. That means leveraging on the fact that not all users or all devices will be connected to the internet at the same time. So we reuse the addresses. So for that purpose, we have the concept of NAT, that is Network Address Translation. It divides the addresses into reusable or private and non-reusable, that is public blocks. So it translates inner private addresses to external public addresses. It hides internal machines from external devices and allow internet access to large number of users via few public addresses. So there are few IPv4 private address which are listed here. That is 10.0.0.0 to 10.25.25.25 and 172.16.0.0 to 172.32.255.255. Then 192.168.0.0, then 192.168.255 to 255. So these ranges of IP addresses are some of the private addresses which are reusable. So this is the basic operation of NAT, that they given the source and the destination ID. This is the source ID and the destination ID. So it follows to the NAT device, and the NAT device sends with the source and destination ID to the public address, it allocates another source address through this NAT device so that it can communicate with the public address. Then this public address again wants to communicate with the source and gives another public address as the source ID. Then this public address is converted into the private address through the NAT device, and it is able to communicate to that private machine. So the working principle is that organization manages internal private network. So NatBoxes manages a pool of public IP addresses. For outgoing connection, NatBox selects one of the IP address from its pool and forward packets from that IP. So how do we migrate between ISPs? So an organization can be connected to multiple ISPs for better reliability. And NAT allows easy interchange between ISPs by changing IP address in the NAT boxes. With these concepts, I think you have already studied in detail in your lectures in NPTEL. Will not go to detail about this. So now we have still, if we use NAT or CIDR, still there are not sufficient addresses which can serve the purpose of the day-to-day devices which are being used. So for that purpose, we introduced the new version of the network protocol, that is Internet Protocol version 6, IPv6. So this is the curve which shows how the usage of number of devices is increasing. So from year 94 till year 2017, this increase is exponential. So why do we need a new IP structure? First reason is that the address space is not sufficient even with CIDR. The quality of service is vaguely defined, so we need real-time service support for modern day application. Thirdly, the mobile applications are unmanageable and there is no direct security support in IPv4. So what are the features of IPv6 is that it provides larger address space. Second, it gives a globally unique and hierarchical addressing. Third, it provides an optimized routing table using prefixes rather than address classes. So the concept of classes is not used here. It gives auto configuration of network interfaces, and it also supports for encapsulation of devices. So service classes are present to support or to manage quality of service classes. And there is built-in authentication and encryption in IPv6 architecture. Also, the IPv6 architecture is compatible with IPv4. So any questions still here? Now we see the IPv6 header format. Yes, so in IPv6, so the current firstly we have this version which is given whether it is IPv4 or IPv6. Then this is the traffic class which is given, then the flow label. Then there is a payload length. Then there is next header for multiple data hopping. And then there is hop limit till which that packet will get lost, will be discarded until which hop. Then we have 128-bit source address and 128-bit destination address and the data. So there are a few extension headers. For this purpose, we use the next header. So this is the additional information which are transmitted through extension headers. So the base headers points to the extension header. So this one is the base header, which points to the next extension header. Then again, next extension header. So by hopping one hop to another hop, we can add another extension if we have more information with it. So IPv6 addressing is 128-bit addresses, which is represented in 8 hexadecimal numbers. So here, this is 128-bit, represented as hexadecimal numbers. So here we can shorten the address. So by reducing, if there are continuous trailing zeros or continuous zeros, then we write it as a single zero. And this address is separated by a colon. So then the leading zeros can be omitted to 0 if there are continuous zeros. Then 1, before 1 we have 3 zeros, it is also omitted as 1. Then after, before 8 where is single zero, it is omitted. And then after it, it is 800, and then there is another hexadecimal number. So also a group of zeros can be replaced by a double colon. Say here is a group of 3 consecutively zeros. Then it is replaced by the double colon and 1. So this double colon can only be used once. So it is not the case that if we have again a set of multiple zeros, group of zeros here, we again add double colon, because then we will not be able to identify there were how many continuous group of zeros here and how many continuous group of zeros here. So that double colon is only used at one place. So there are a few prefixes which define the address space allocation in IPv6. As we have seen in classless addressing also, based on that prefix, we decide the class. So here, if we have this prefix with all the 8 zeros as zeros, these are the reserved spaces, and the start of that address ranges from 0/8, and it is the fraction of the address space is that 1 by 256. So another, if we have all the 4 zeros and 001, that means it is reserved for NSAP. Then if we have 0000010, it is reserved for IPX. And then there is global unicast, which is 001. Then there is link local unicast with this prefix, site local unicast with this prefix, multicast with all ones. So total allocation is 15% of the total address spaces. So there is enormous amount of space which is still left. So these are the things that you need to remember when you start using this address spaces. Okay, thanks. Thank you for this lecture. So if you have any queries, you can ask. So then we can have the discussion over a set assignment, which is similar to the assignment that you'll be given in this week. You are already been given. Okay, if you are having no queries, so we can have the discussion over the assignment. So please solve these questions. I'll give you some time. And if you have any questions or queries, you can ask. I will discuss the solution as well. So first question is, what are the maximum number of hosts which are under class B addresses? How to find subnet mask of any IP address. So if you are given the IP address, so for subnetting, you will be given a slash. That means that what will be the bits which are occupied for the host IDs. So say 208.125.255.255. Okay, dot 16.0. Okay. So here, if it is given /16, that means the initial 16 bits are occupied for the network ID. So the subnet mask will be all ones in that case of 16 bits in the initial 16 bits. That will serve as the subnet mask to that particular network or to that particular IP address. So how many maximum number of hosts which are available in class B, which are possible? Akshit, I hope it's clear to you how to find that subnet mask. You're given with the slash and the bits which are occupied for the network ID are all set to 1 for the generating the subnet mask. Please answer these questions. What are the maximum number of hosts possible for class B addresses? So just answer me this question that how many addresses are reserved in case of this IPv4 classless addressing. The special reserved address. That means this network ID and the broadcast ID. So as I mentioned, there were two reserved IDs. That is one for the identifying the network and another for identifying this. No, I'm not asking which class. That is class E is for the reserved addresses. But I mentioned explicitly there are two special addresses. One is this network ID and one is for the broadcast ID. So these two are not used for the cases of representing host numbers. So for that purpose, the answer of Fizza is right. It is 2 to the power 16 minus 2, that is 65534. So all of you other who have given 653536, please understand this concept. So there are two addresses which are reserved for the network ID and the this broadcast address. So that is not used for the host, total number of hosts. Okay. Anyone having any query here? You understood the answer or the solution? So another question, what is the maximum number of networks possible in class C IP address? Networks, understand networks. Number of networks possible in class 3 IP address. Yes, so in class C, there are 3 bits which are reserved for identifying the class C, and the other bits out of 20, this 24 are reserved for um, this network ID. So the total number of bits are 2 to the power 21. So we have in all 24 bits, and out of these 3 bits are reserved. So then it gives the answer 2 to the power 21, not 2 to the power 24. So next question is, suppose that computers P and Q have IP addresses 10.20.5.225 and 10.20.5.9 respectively, and they both use the same net mask n. So which of these will be the value of n given below should not be used if P and Q should belongs to the same network? I remember that this question we have already solved in the previous first lecture as well. So I'm giving you 5 minutes of time to solve this question. That it should not, P and Q should belong to the same network. That means their network ID should be same. I'll give you a hint. So these are the IP address to P and Q. So whenever we do the ANDing with the subnet mask, that means AND operation with the subnet mask, it generates the network ID. Okay. So we have to check whether the network ID for both of these are same or not. So for what values these are same or not same. Just try to solve it. I'm giving you 5 minutes of time. Anyone is able to solve, please reply. Okay, I'll give the solution. So the correct answer is D. So as I give the hint that this is the individual given subnet mask or net mask, when you do the AND operation, that means bitwise AND operation with this IP address, then you will generate the network ID. So again, you do the bitwise AND operation with this IP address, you will generate another IP, and you check if both the IPs are same for this. So both the IPs for this will not be same. Similarly, in this case, it will not be same. In this case, it will not be same. For this case, it will be same. So here both, okay, sorry. Uh, Yeah, so in all these three cases, it will be same, but then the last case, it will not be same. So this cannot be used because we want PNQ to be on the same network. Yes. So for all these cases, this is the network ID generated, but for the last one, the network IDs are different for both of them. So what is supernetting? Splitting the large network into multiple networks, combining multiple small networks into a single large network, enables the network to accept more hosts or connect a new network to an existing network. Yeah, so correct answer is B, combining small networks to a single network. So which of the following is not a valid IPv6 address? Okay, so the correct answer is D, that this is not a valid IPv6 address. This is only 4-bit hexadecimal number. This is a 8-bit hexadecimal number with double column. So this is all zeros. So this is again 1, 2, 3, 4, 5, 6, 7, 8. 8-bit 1, 2, 3, 4, 5, 6, 7, and this is one double column which is composed of 0. So only the last one is not the correct IP address, which is true for class E. It is used for multicasting. It is reserved for experimental purpose. It is used for network with numerous hosts. It is used for network with less number of hosts. Yeah, so correct answer is that for class E, it is reserved for the experimental purpose. Okay. So next question is, what is the possible IP address ranges for class B? Okay, so for class B, the first two bits are reserved. So that is 0, 1, 1, 0. So the correct answer is C. All the other bits are 0. So it is 128.0.0 to 191.255.255.255. So next question is, you need 500 subnets, each with about 100 usable host address per subnet. What network mask will you assign using a class B network address? That means 500 subnets, each with 100 usable host address. Okay, so the correct answer is B, neither C or D. That means the class B default net mask is 255.255.0.0. So to have 500 subnets, 9 more bits are required to be included in that subnet mask, because class B has 16 bits reserved for that host network ID. So that subnet mask is all ones. And to have 500 subnet, 9 more bits are required in the subnet. So that subnet mask will be 255 again, and 1 bit as this one. So this will be the total number of, so this will be the allotted subnet mask. That means all ones, and this one as the ninth bit. Each net mask has 7 bits for the host part, which are sufficient for 100 hosts. I hope everyone is clear with this answer. So next question is, the header length of IPv6 datagram is. Yes, so the header length is 40 bytes in IPv6, right? So we write the IP address as 191.180.83.235/12 in CIDR notation. What is the subnet mask to that particular IP address? So the correct answer is A. I don't know how you're all giving it D. So it is /12. So the first 12 bits are the network address, and the rest 32 minus 12, that is equivalent to 20 bits, are for the host address. So for IP, this binary value, subnet mask will be 10111. This will be the subnet mask. It is all ones for the initial 12 bits. That is equivalent to 255.240.0.0. Okay. So that is it for today's lecture. If you have any queries, you can ask me. Stop sharing screen. Yeah, I will share with you in these this networks files. I'll create this teams. In the teams, there is a folder called files. So I will share those assignments in that corresponding folder. You need to practice the questions and understand the concept. Then only you can increase the score. Okay, if we are done, then you can leave the session. Thank you all for attending. So I'll end the session now.